So today we'll talk about bilinear transformation. So to get you familiar with S domain to Z domain, and we can translate all the continuous time filter knowledge to discrete time. Then we'll do a first order example. Okay. So let's first talk about the bilinear transformation. Okay. So So bilinear transformation is starting something to from continuous time to discrete time, and vice versa, right? So it's like transferring between. So discrete time usually you say something S, right? And discrete time you say something in Z, right? So 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 there is the Z is defined as e to the s of t, right? So basically, let's say if you have a time domain waveform, something like this, and you're uniformly sampling it to get all these samples, right? So this will be your continuous time waveform, and these dots will be your discrete time samples. Okay, so this is your continuous time, and this will be your discrete time. So you will have this, this, and this. Okay, so so there is an important theory called sampling theory, right? So basically it says because of the sampling nature, right? So if it's a sinusoidal, right? Okay, if you so if you have a sinusoidal, right? For example, something like this. Okay, now if you so this is your continuous sine waveform, right? Basically, it's a sine wave. So and the highest frequency in discrete time is something like this, right? So that's what you can have, maximum frequency. Okay. If it's DC, in discrete time, it will be just everything here, right? Everything same. So that will be your DC signal, very low frequency. So if it's like +1, -1, +1, -1, +1, -1, so this is the highest frequency. Okay, so as you can see, there is no highest. So the highest frequency in continuous time. So this is continuous time, and this is discrete time. The highest frequency is actually infinite, right? You can describe using like 10 gig, 20 gig, etc., right? So there's no limitation on the highest frequency you can represent. So, but the highest frequency of the discrete time system depends on your sampling rate, right? So if your sampling rate is every 1 nanosecond, right? This is 1 nanosecond. So the highest frequency is half of your sampling rate, right? Because so from here to this point, it takes you 2 cycles, right? 2 sampling times. So highest frequency is half of your F sample. Okay. So this is so-called Nyquist theory. So basically, what it says is if it's a sample system, the highest representable frequency is half of your sampling rate. You cannot get higher rate than 1 minus 1, 1 minus 1, 1 minus 1. Well, that's what's saying. Okay. So what if it's actually you have, okay, let's say for example here, you're sampling something like here and here. Okay, this is and sampling here, right? So let's say this is 1 nanosecond and this is another 1 nanosecond. So what if you still have have higher frequency? Let's say so this is this will be your if it's 1 nanosecond, then that's 1 gig, right? Nano is 10 e minus 9, and 1 over 1 to e minus 9 gig, right? So then what if I have double the frequency? So let's say what if I have something if I double the frequency, that means I have to reach here, something like this, right? So instead of within the 2 nanoseconds, instead of having a 1 period, I'm starting to have 2 periods, right? So what you see, if I still sampling here and here and here, what I'll get is 1, 1, 1, right? So it becomes DC now. So let's say, so your original frequency is 500 meg, right? So basically your F. So let's roll here. F sample is 1 gig. So if your signal is 500 meg, so you get 1 minus 1, 1 minus 1, right? So this is correct, right? So F6, if it's 1 gig, then what you get is 1, 1, 1, 1, 1. So this becomes easy now, right? So again, if your F signal, what if it's 1.5 gig? So that again, if it's 1.5 gig, it will represent to 1 minus 1, 1 minus 1. So you'll see basically if you have a sampling rate 1 gig, okay, and you have multiples of 1 gig, 2 gig, etc. So if you have a spectrum of something like this, right, and if you have something like this, okay, this is a signal spectrum. So then this part will be folding back to here, okay. So your 1 gig will become DC, and 2 gig will become 1 gig, okay. Oh, sorry. Let me rejoin. So let me rephrase what I said. Okay, so this is your 1 gig, and everything is symmetrical about the half of rate. Okay, so let's say you have some spectrum like this, right? This is your original signal. What if you have another signal, something like this? Okay, so what that will do is this will fold to here, and this 1 gig will fold to here, right? So you have something called spectrum folding. So again, similarly, so those between 1 gig and 1.5 gig will also be moving down to this part. So and will be folded to your existing spectrum. Okay. So basically, what I'm saying is, if sampling rate is 1 gig, there's no distinguishing. You cannot distinguish between 500 meg and 1.5 gig, DC and 1 gig. Okay. So let's something about we talk about spectrum folding and Nyquist theory, sampling rate, etc., etc. Right? So we usually describe our filters, right, in continuous time like h of s, right? So we usually have a cutoff natural frequency of omega 0 or something. So then we need to translate to a so we usually denote this as large or big omega, and this will be h of z, and this is h of s. Okay, so we need to translate between this to this. Okay, so this is starting from our bilinear transformation, which is defined as, because z is defined as e to the s of t. Okay, so that's the definition of z, right? So that will equal to e to the s of t over 2, e to the st of minus 2, right? So, and then we know e to the x will roughly equal to 1 plus x, right? So that will equal to 1 plus st over 2 and 1 minus st over 2. Okay, so again, so if you rephrase to organize a little bit, so this is how to translate from z, so z to s is something like this, right? 1 plus st over 2 divided by 1 minus st over 2. Okay. So so if for a fixed system, right? For a fixed system, we usually denote as the sampling rate is fixed. We denote this as s prime. So basically, z to s prime is equal to 1 plus s prime, 1 minus s prime. Okay. Now, so we then need to figure out from s to z, right? So again, we usually ignore the if we define it this way, so then basically z minus zs will equal to 1 plus s prime. So z minus 1 will equal to 1 plus z of s prime. So s prime is equal to z minus 1 divided by z plus 1. Okay. So that's the two translation equation. So if you know one, you can figure out the other one, right? So the only thing noticeable here is we introduce a s prime, which is defined by s multiplied by half of t. Okay, so that's the only difference. We just scale everything of s by t over 2, and t is your sampling rate, and you should know. Okay, so this is how do we translate the s and z, right? So there's one thing also we needed to be familiar with is the frequency wrapping, right? So we needed to see the corresponding what's the frequency here corresponding to a frequency here, right? So this is omega 0, because these two numbers are different. They're not on the same scale. Okay, so this one has a maximum of half, right? 0.5, because if bigger than 0.5, then if it's bigger than 0.5, it's symmetrical, right? So so we are not interested in something bigger than 0.5. Oh, sorry, is 1. Because because everything besides that one, so that should be in terms of it's 0.5 multiplied by 2 pi. Okay. Because your maximum is half of the sampling rate, right? And it's expressed in radians, so it's 0.5 of 2 pi. No, but this one has no limitation. You can go infinite, right? So how do you map an infinite number to something between 0.5 multiplied by 2 pi? So we can derive, and actually there is a formula. So basically the omega of z in terms of z is actually 2 over t of tangent of this one. Oh, sorry. So this is omega, is this one. So 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 if we still so if we still keep our definition of S prime is equal to half S divided by T over 2, right? Sorry, S is S multiplied by T over 2. Okay, so everything here will be this guy multiplied. So omega prime will be this one times this one, so that get cancelled. So this one also the half of t is there. Okay, so basically we multiply everything by t over 2. Okay, so let's take a example. Okay, so so again, so if we use this transformation, so here then we're assuming t of 1. So so this will be half of the original omega. Okay. So let's say if you have originally for the case where we have expect something like originally you have a so you want something like this. So you want something you have want to have a cutoff at 30 kilohertz. Okay, and this is your continuous time model. And right now, so you want to translate this to a sampling of rate of 1000 kilohertz. You wanna see this is, so you wanna see what's this one, right? So basically what we can do. So sorry, let's say 10 kilohertz. Okay. So uh, so let's see. First, your 10 kilohertz over your 100K. So that's 0.1, right? So and multiply. So this is your f. So this is your f 3 dB in Z domain, right? In this Z domain. So omega of 3 dB will then be 0.1 multiplied by 2 pi, right? So that's 0.2 pi, right? So so basically you want something like 0.2 pi, and so below the pi, right? So what's this 0.2 pi translate to? Okay. So then we use the formula, right? So basically omega prime will be tangent of half of omega. Okay. So that will give you because this is normalized to normalized to a T of 1, right? For easier manipulation. So then so this will be tangent of 0.1 pi, and this is how much? 0.3249. Okay, so this is at the omega of 0.3249. Okay. So so then we have a pole. So our pole will be at if the first and second will be at 0.3249. Okay. This is not a is not a real the true number, because everything has to multiply by t over 2, right? Kind of remember. So it should be like kilohertz or something, right? So the real number is because s prime is s multiplied by t over 2, right? So then your s is actually at s times 2 divided by t. So that's 2f of s prime, right? So that will be 200k multiplied by 0.3249. And that's your real pole location. But so because it was based on the based on the real so this is the minus one, right? So based on the normalize normalize everything to multiply by T over 2. So it's that as this and here. Okay. So now so if the pole is here, so then we have a formula, right? So it's S, so it's 1. So it's like 1. The formula H of S will be 1 plus 1 plus S divided by omega, divided by omega p, right? And the omega p is this one, right? So this one, you use this one translate in bilinear. So translate to an h of z, right? And so that will translate to so we know if your S is at this location, right? The pole is at this location. You use the bilinear, so Z will be 1 plus P divided by 1 minus P. Okay. So that gives you 0.5. 0.5095. Okay, so then your h of z will be something like 1 minus so will be z minus 0.5095, and this can be 1 if you don't have nothing, no 0. Okay, if you have 1, you want to have a alternation high frequency. So then you want to have a 0 at minus 1, so that will be z plus 1. Okay, so this one is to give you a 0 at infinite. So this will be translated to z minus z at minus 1. So that's translated to a z plus 1. Okay, so that so far what we have learned, the bilinear transformation. So so then we can look at the example shown there. So then we can have something similar to this, okay, for a Z domain. For a Z domain implementation will be something like this. So we have an R and C, right? So this is C, and this is R, and this is R, and this is C, right? This is providing the 0. This is providing the pole, right? So so we replace everything, replace the resistor with our switch cap approximation, right? So that will be this is P1, P1, P2, P2. So similarly here, P1, P1, B2, B2. Okay. So so let's say this is C1 and this is C4, C2 and C3. Okay. So C2 and C3 to mimic the resistance and the cap, with two resistance. C2 and C4 is to use to describe the 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 original cap there. Okay, minus plus output. So then we can use something called signal graph, right? Signal graph. So if you're using signal graph, you're assuming everything is here and is starting together, and it's processed by something like 1 divided by C4, and there's a and this is output. Okay. So if you have this branch, then you don't have. So if you have this branch, then you have the. If it's this one, then it's purely C1, C2, and in here, oh sorry, it's a minus C2. Okay. If you only have this one, you only have C1, then you have the minus C1 of 1 minus C1, okay? And again, here, this is feedback from the out to this one, right? So you have that one, so that will be minus C3, okay? So this is describing this path is here, this path is this one, and you have this one, it's from here, okay? So this is the in, and this is the out. So here then will be, what's the voltage here? Will be C4 of 1 minus C1 V out, right? So that is equal to 3 summing together. So C4 1 minus C1 V out will equal to this one, right? V in of minus C2 V in minus C1 V in 1 minus C minus 1 minus C3 V out, right? So then you will have an edge of Z will equal to V out over V in, right? So you push all the V out to one side and push the V in to one side. So V out will be C4, C4 minus C4 V minus 1 plus C3. Okay, and this one is minus C2 plus C1 1 minus D minus 1. Okay, something like this. Okay, so so this is your so if you multiply everything by Z, so this one will be minus C4 plus C3 of Z minus C4. So sometimes you want to move the C4 out. So you want to get some so that will be your formula, and if you organize, so then you'll get 1 plus C3 divided by C4 minus multiplied by Z minus 1, and then this is C4 of C1 plus C2 and of Z minus C1 divided by C4. And this is whole thing a negative 1. Okay, so so that's what I want to say about signal graph and the first order. Okay, so that's so much for what we want to talk about. So let's show you how we can do a bilinear transformation, how we can derive a switch capacitor implementation and get the signal graph and get the final filter equation. Okay, so that's all for today.